Hey, welcome back to the Engineering Dynamics Course Companion. We're in Class 20. We're now into Kinetics of Rigid Bodies. This is Newton's second law in constrained plane motion. Yes, so Class 20 out of 24. As with all the videos, you can go down to the description below and click on the link to go directly to the example. I think that's actually only true if you're using a web browser, though. I think if you're using YouTube on a phone, that's not available to you. So that's going to be interesting for people. All right, we're going to do the bottom line up front. Okay, so rigid body motion in kinetics has both translation and rotation. All right, so that's what we know about rigid bodies, right? They have translation and rotation. So in a similar manner, when we go to the Newton's second law for the thing, we have F equals ma for the translation side of things. But then we also have a corollary to F equals ma. And we're going to deal with the rotation, so we have moments. Right? If you remember from statics, we applied forces onto objects, and that could create a moment. Like force times a perpendicular distance creates a moment. So we have the sum of the moments about the center of gravity equals the mass moment of inertia about the center of gravity times the angular acceleration that we'll call alpha, and we note that those are vectors, right? And we know, and take a look at those side by side with each other. We have load is proportional to motion, proportional by inertia, right? So we have here, we have load is proportional to angular motion, rotation. So the rotational load creates the rotational motion, and it's proportional to it by the mass moment of inertia, right? But we have to be careful. Some problems, it's not going to be the best to take the moment about the center of gravity. You remember from statics that a lot of times when we're trying to solve a problem, we can actually move where we're taking the summation of moments about based on the geometry, but also as a simplification. Sometimes it's just necessary to take it about a point that is not the center of gravity. So, and for a more generalized equation, we want to say that the sum of the moments equals the sum of the effective inertial moments, right? And so we'll define what that is and describe it. And we'll see, actually, when we go about doing that actually will demonstrate the parallel axis theorem and how that parallel axis theorem works. And we could see that when we use kinetics later for work and energy and for impulse and momentum, that happens in each of these. Okay, so we're going to apply Newton's second law to a rigid body. Here, Newt Dog, I am sitting on top of a beam, and I'm going to cut that cable. And what's going to happen is there's going to be impending motion. So there's actually going to be an acceleration because there'll be a velocity an instant later, therefore acceleration. And we could work through, that's a very a typical problem, a classic problem. But here on our boomerang, just as a generic rigid body, we have our forces that are applying to there. Where, once again, those forces create acceleration. And we have the sum of the forces equals mass times acceleration. But now we're going to add on the moment, some external moment that's taking place to the thing. I don't know. Somebody came from the outside. They put a drill onto the thing and force the thing to start spinning. And that's going to create I alpha gets placed on the IBD side, right? So once again, that diagram represents the FBD and the IBD. We have the load side and we have the motion side right here. And here is the FBD and the IBD of that, what would be taking place. And we're assuming here, I went ahead and assumed that Newton's weight was inconsequential, so I didn't include him on there. But you could see how this is going about. We have the motion that's taking place, right? It's going to be acceleration downwards, and we also have the angular acceleration. So one scenario that can happen is we could have something that now is going to be about a fixed point, right? So now if this thing is moving, maybe we clamp a hold of that thing, and now this thing is going to be rotating, but this stays fixed. So instead of taking the moment about the center of gravity, it's probably better to take a moment about where it's fixed, right? So now we have to have the effective moment about that point where it's fixed. And so what that's going to end up having is, all right, so if it's fixed down here and I'm ghosting in the location of the fixed point, you can see the reactions that are right there. And there can also be an external moment being placed right there. But if we go over into the right-hand side, so we'll just say that these are all the things that are taking place, that we can now have a mass, this guy right here, that's happening. That's part of our effective moments, but also this mass times the acceleration, right? Well, I guess it's this one. It's the first one I drew, times this distance, right? And so so this is like an inertial force, but together that's an inertial effective moment, right? Because you have to have that inertial effective force is going through the center of gravity, and that doesn't align with the point about which this thing is turning. And that's also true in the vertical direction right there, right? So now we have this inertial force, mass times acceleration, but we also have a distance that we have to consider. And it's the distance that's perpendicular to the force. So that's what we mean. And so, but what we could do instead of this, right? All right, so that is one of our alternatives, is to say this effective. But now instead what we could do is we could just say that it is the moment of inertia about B. And what we've really done is we've moved the moment of inertia from the point about the center of mass, and we've moved it downwards. Whoops. Let's see, I think on my next slide, I'm actually going to show mathematically where that happens right there. But what we're really saying is this is going to be, as a big equation here, times alpha, we're going to find that it's going to be plus this distance that the thing moved, right? If that's d, so it's going to be md squared is what we would do to get that IB, right? So that new IB is equal to the mass moment of inertia about the center of gravity plus the mass times the distance that it has to travel to get to there, squared, right? All right, so, yes, okay. And my computer has just a little lag, and there's a little IBD floating out there in space. All right, so the parallel axis theorem, like as I just alluded to, can be revealed by taking a look at this right here, right? So as I said before, the mass, the effective inertial moments right there are written out right here. But if you were to take and just say this, right, if we were going to combine that AT right there, right, that's going to be the tangential one, or it's going to be the acceleration that's going, one of the only accelerations, that's the acceleration that's going to be perpendicular, I should say, to the thing. That is going to be I alpha plus that mass times that tangential acceleration times that distance that the thing has to move, right? Well, that we know that the tangential acceleration will just be alpha times that rg with respect to b, right? And right here, you can see that right there is going to be the parallel axis theorem, right? Just by taking and substituting in that the idea that the tangential acceleration, the acceleration of these two, of that motion of the center of gravity, is going to be right here. Okay, and by the way, that's the only one that has a mass. Okay, we might also have a normal component right there, right? You could say that, but that one doesn't actually move. It doesn't move towards the. It doesn't change its in the normal direction, right? It's only the tangential one that can move because it's fixed about a point. right? It will affect the reaction forces. So the reaction forces will be equal and opposite from the normal, and well, we could find in the tangential what the reaction forces are going to be based on the tangential. But in terms of actually creating a moment that's going on here, it's the tangential we're going to care about. And well, we can make the equivalent simplification of just taking that IB times alpha. Does that make sense in terms of the mass moment of inertia and how the parallel axis theorem can be found, right? So here you go. Parallel axis theorem is that right there. Okay, so here we have an example. Here's a drawbridge, and it's got a length of 5 meters, so that's pretty long. What's that? That's a little bit more than 15 feet. And it weighs 1,000 kilograms. And a single cable is used to attach to the end right there. And at the moment shown, it's 45 degrees. Starting from rest in the position shown, the winch pulls the cable at a constant tension of 10 kilonewtons. We want to find the acceleration at point B. And we also want to find the reaction forces at pin O. All right, so one of the first things to do, take care of, get the mass moment inertia of the drawbridge, right? So we know for like it's thin and slender, we'll assume that its thickness is small enough in ratio compared to its length that we don't need to use the rectangular one. We can just use the thin like rod or side of a plate designation. So that's 1/12 ml squared. So we go ahead and put those in, and we find that, and those units are kilogram meters squared. Now let's take it about O, right? So we don't necessarily have to do it. I think I do it two different ways. So we'll do it the first way. We'll just find the moment of inertia about O using the parallel axis theorem. So we take in and we moved the center. The center of gravity is about that this guy is right here, but we want it about O, so we move it 1/2 of the length, or 5 divided by 2, and you can see it's a considerable amount. A lot of times you will find that when you move something, it has even a large effect on the overall moment of inertia compared to what the moment of inertia is about the center of gravity. Okay, so one of the very first things we'll do after taking care of some of that business is the FBD, IBD. It's a really good idea to draw those right away, maybe even before doing the mass moment inertia. We just want to make sure that we're very focused on this free body diagram and inertial body diagram. So we start putting the external loads in there. We've got to remember that gravity is an external load, even though we think about acceleration. No, don't think about the acceleration. It does not belong on the IBD. It is an external load, the Earth pulling this thing down. And now we have the tension that's taking place from the cable. And then we also have these reaction forces, which we don't necessarily know the direction of them, but we're going to draw them in the positive direction. And then we go over to our IBD side, and then the only inertial effective force that we have to put on there is the moment of inertia, mass moment of inertia about O times alpha, right? We don't need to double down on here. Now, we could actually, I might want to, when it comes to my reactions, go ahead and put them on there, but I want to leave it for just now without putting that mass times acceleration on there, because you don't want to double dip, right? That's one of the reasons why we had that previous explanation about using the parallel axis theorem and how that's built into there. We don't want to double dip and also include the effective mass, the effective inertial moments when we've already taken care of them by taking the parallel axis theorem and shifting the thing out, right? So we put in these loads, and we notice that we make sure that we're only taking the part of this tension that is going perpendicular to the moment arm, and that the moment arm in this case is L long. And also we have keep the signs correct, where we assume that counterclockwise is positive, so it's negative because it's going clockwise. And then we also include the mass times gravity, so the weight of the thing, and that's by a moment arm of L over 2. And then we recognize that it's going to be accelerating and causing it to go in the clockwise direction. So by putting in the things that we don't know about this, right? So the things that we know, excuse me, and we can find what alpha is going to be, and it's 1.3 radians per second squared, and that's going to be clockwise. If we want to find what the acceleration at point B is, we can just get the magnitude by simply multiplying the angular acceleration by the length of the thing. So 1.3 times 5, we get, and there's some a round off going on when we had the 1.3, so it ends up being 6.498 meters per second squared. So 6.5 meters per second squared upwards is what the answer to part A is going to be. Now when we want to do the sum of the forces in the x direction, I have to say that I'm a little concerned about this right here. Okay, well, for one thing, okay, this is true. It is going to be 0 here because right here in the position shown, there is 0 amount of velocity. If there had been some velocity, we would need to come over here and add in mass times the normal acceleration, right? Because remember, that right there would be v squared over rho, right? But since there's no velocity going on right now, we could go ahead and say, well, the normal acceleration. Oh, by the way, we might even want to say that this could also be omega squared r, right? That's another way that would also be happening, and it would be happening in this direction, in the normal direction, right? So that would influence what the reaction was at O. But because it's just starting here, it doesn't have a velocity, therefore it doesn't have any normal. But we have to be careful in the y direction right here, right? We didn't draw this thing on here, and perhaps we should have, right? We should have drawn mass times the acceleration in the tangential direction. I said it is, I guess we could do it in the y direction right there. And I didn't draw it on my free body diagram, and it probably should have been, but I didn't draw it, I think, because I didn't want to people to double dip, right? But so that was a mistake by not having it on there. But anyway, we go ahead and we take a look in the y direction, and here that's going to be positive because, yes, it's going upwards. The weight's downwards. And here's the reaction that I've drawn upwards. We don't know that it's necessarily upwards. And here's the mass times the acceleration in the y direction, which we know to be alpha times L over 2, right? And get rid of some of that stuff because it's in the way. And we put all this stuff in here, and yes, we get 5,990 newtons going upwards. So that's what the reaction is. But now let me redo the problem here and use the effective moments, right? So we went ahead and we did the parallel axis theorem to bring the thing about point O. But now let's do the effective moments right here, right? So we draw these in here, right? And now we also put in the mass times the acceleration in the center of mass, which we honestly should have put in there anyway. And by the way, this thing kind of shifted down, so that should be I about the center alpha right here. And some of the effective moments, you can see that we're still taking the moment about O because we want to get rid of those reactions when we first apply the thing. But now you can see that we have, not only do we have the I alpha, right, and that right there, by the way, that should be this right here. So that's a mistake. That should be I bar times alpha, and we also should have the mass times the acceleration at the center right there, right? But we know that we can go ahead and substitute the acceleration at the center of mass is alpha L over 2 right in there. And so by substituting that in and then plugging all the values that we know about the thing, we get the same angular acceleration. And we'll get the acceleration at B like we were asking for. So that's the same result. So for more examples, on this subject and for all the other ones that are here, we want to check out the Engineering Dynamics Course Companion Parts 1 and 2, and we're into Part 2 now. This is Class 20 we just covered. This is published by Morgan and Claypool Publishers. Follow the link down below to get to the publishers. You could purchase the book. You could also find it on Amazon. And please subscribe to this channel because more videos will be coming as we progress. So thank you very much and see you in Class 21.